So, Bismillah wa salatu wa salam ala Rasulullah. So, when we talk of a supervector machine, it is actually made for two-class problems. So, supervector machine is made for two-class problem. So, how does it work? So, let's pay attention just to the secret of supervector machine, which is what I want you to get, which is very important. Supervector machine always believe that you can draw a kind of separating hyperplane between any two classes. See, it always targets that if you have two classes, you can always draw a line between them. Once you draw the line, the next unseen data, once they'll be able to belong easily without any issue. And that actually happens to be the major limitation of supervector machine because it doesn't have the capability to solve three-class problem directly. So you have to use an indirect method to solve multi-class problem when you are dealing with supervector machine. Because of this, we cannot really, we say this is the weakness. It cannot solve three-class problem directly, but then it has a way of doing it indirectly. Now, so the idea of supervector machine, summarily, is that it always believes you can draw a line, this line. I hope you can see my screen. Am I right in there?
Yes.
Okay, you can draw a line between two lines, to separate two classes. So, and then, of course, this is the equation of a line, which is, so we have the weight we already mentioned. W is the weight of the vector. X is the input value, and B is the bias, just like we explained in the case of neural network. So when we have this case, once you draw a line, then you keep increasing this line. You keep increasing it. We create a margin. You want to get a maximum margin. What is the maximum margin possible? Before you start touching one sample from this side and also this side. Because there are several lines you can draw. I can draw another line. If I ask you to draw a line between these classes, there are going to be thousands of lines. This is my own. Mohammed might decide to draw his own here. Another person decides to draw, a little bit slanting. So we have several possibilities. So you have to, anyone you draw, you have to try to increase the margin. Before, the moment it touches one here or more, you have to stop increasing that margin. So the line that gives you the maximum margin before touching either side is known as the maximum margin hyperplane that we're going to select. So, so the moment you have that, we have in this class greater than 1, which is going to be to the other one class, less than 1, that's going to, or less than or equal to -1, that will be the second class. So this is two-class problem, which is what supervector machine is noted for. Now, so the distance from an object to the hyperplane, the one I'm just explaining, is given by this formula. So because we're only using this diagrammatical representation to make you understand it. In real life, you just have your data. So there's a way to compute it. Using this formula, you can easily compute which is going to be having the larger margin, which is the maximum margin we are looking for. Now, once you try, you start pushing up this particular margin. Those ones you first touch, you can see from this red class, we have this one and this one. From this side, we have this one. We couldn't get two. You can get as many as possible, but then for this particular maximum margin we established, it is only one here, two here. These guys, they are referred to as support vectors. We call them support vector. They are the closest object to the hyperplane. The closest from either side, from either of the classes to the hyperplane, they are known as the support vector. And they are very, very important. Actually, this algorithm got its name from them. That's why they call it support vector machine. It is a machine that works on the principle of support vectors. Once you get these support vectors, colors, your work becomes very easy. Because when we are going to have a test case, you need those support vectors you got during the training phase. You need them to be able to execute your test prediction, testing set prediction. So now, so the width of the margin we are looking for is the width of the boundary that could be increased before hitting the data point. This is the idea. And it's given by this formula. That is, What is the width? We can increase you before you hit a point. What is the here? And we want the two sides to have the same equal width, equal distance, almost equidistant. A little bit of difference is okay, but you should not be too close to one at the expense of the other. So we say the maximum margin linear classifier is the linear classifier with the maximum margin. That is, it's linear in the sense that this is the original data you give to me. I can easily draw a line. But there are situations whereby you cannot draw a line between them. It's not possible, no matter how much you try. We call them non-linear problems. We are going to get to that, inshallah. So in the linear SVM, mathematically, you see we have, this is the line, the separating hyperplane we talk about. This is the margin we created this margin. So here on the line, you have that equation is equal to 0. AI is equal to 1 for this class, plus 1 class. For the negative class, we set it to -1. So this is what we know. Consider these two equations. This one equal to +1, this one equal to -1 mathematically. You did linear algebra. Only through the dot product of these two equations you can have, you can arrive at this equation. And from there, we can get this particular value if you make M the subject of your relation. M is the margin. This is the margin we are looking for. That big M is the margin. The distance between this and this after we try to increase it. So it could be, this is given to be equal to, and what we got here, we can be able to get out our M, which is going to finally result in the formula we got earlier, which is the margin. This is what we are looking for, the maximum margin for every data that we have. Now, if the training set is linearly separable, so binary classification can be viewed as the task of separating classes in feature space. See, this is the very simple stuff. You just draw a line between them because they are linearly separable. The data is very cooperative. So this is what I was explaining before. You can see this guy. Can you see? I can draw this line. This is from Adam. This is from Sharif. This is from Muhammad. This is from Imran. So you have so many possibilities. But then if you look at this particular line we are drawing, Shabab, you will see that if I choose this line, it will not give me equidistance. You can see. It's too close to this guy. So we are going to say, no, we don't want this line. You look at this line, it's too close to this guy. So you are going to look for one line that is what we are looking for, where we use the upper surface equation. So after doing that, already our formula is there for us. This is the one we just derived. So you have it here, you increase the margin, you can see. These are the distance to that point. So the first one that this margin is pulling against, we pick it, this support vector for this guy. This guy is having 2 support vectors from inside. This one also can have multiple. But you don't say because you want to have multiple, you compromise the optimal hyperplane. No. What you just need is at least you need 1 support vector from each side. Once you get 1, it's enough. But if you happen to get 2 like this, that is excellent. So once you get that, then the support vector are gotten. So you can see the distance, this distance we're measuring. So, yeah. So the linear SVM mathematically is given, it's an optimization problem, just to let you know this. So because of time, so I'm not going to be asking you to prove this one this time around, but at least have an idea of how it works. Are you with me, by the Shabab?
Yes.
Okay,
Yes.
yeah. Yeah. I know everybody's under pressure, don't worry. So we just need to have an idea of it later. You can go deeper and also try to see some of the mathematical basis. So one unique thing with support vector machine is it has a very deep mathematical background. So for the support vector, we've gotten that support vector. So the problem could be better formulated depending in minimize. You are trying to solve this problem, find W and B such that this is equal to this, which is minimized for this. So it's a minimization problem. So we're looking for W and then the particular H. Solving the optimization problem, surely there are different ways to solve the optimization problem, as I mentioned regarding description of techniques. One popular way is you have the primer form, you establish the primer form, you solve this Lagrangian formulation, and then from there you have the dual form. So which is going to result in this kind of optimization problem under constraint, in which case you solve an optimization problem for support vector machine. you can see that compared to neural network is just talking of, if you remember, sigma wi times xi, simple, just arithmetic. But for support vector machine, no, it has a lot of quadratic optimization problem. And that is one of the challenges of support vector machine. It takes a lot of time to run, especially if your data is very huge. And I'm going to tell you another reason why it takes time to run. So this is how you find a solution. So an analogy to support vector machine, try to say, okay, can I find a solution at this level? If I cannot find a solution, can I move to a higher level? Hopefully at the higher level, I can get my solution. When we're going to deal with nonlinear situation, you appreciate it better. So in essence, we're saying that the classifying decision function is going to be given as this. So once we're able to solve the optimization solution. And then an example is given here. So you have a case, she's trying to see these are three inequalities that are brought out of it. So for this equation, you can get the inequality using the cont'd condition. Implies this equation also can be proven from where we can solve for the values that we intend. Now, so for the dual problem formulation, it is given thus. So you have the dual problem formulation, and then which is finally, you want to maximize these subjects to this. When you say maximize or minimize, then you're talking of optimization problem, it's quadratic equation problem, so which could be solved in different ways. This is one of the ways we can use to solve the problem. So once solved, know here the eigenvalue and the eigenvectors and what is involved. You solve for the appropriate values. This is optimization problem. So in summary, the optimization problem you want to solve in support vector machine is maximize this subject to this, where C is the penalty for error, the C, the cost. This is very important parameter, hyperparameter that you need to solve, you need to optimize in support vector machine. So, and the solution is given by this, where n is the number of support vector. You see, n is the number of support vector. So n is very important. The number of support vector, with those support vectors, you cannot solve for the testing cases. So that is for linear. Now, let's look at nonlinear SVM, Shabab. For nonlinear SVM, what we are saying practically is this. Look at this problem. We say this data set is linearly separable. This data set is linearly separable. What does it mean to say that it is linearly separable? It means that while this one, I can easily draw a line in between. I can easily draw a line in between. This is class, red class. This is blue class. I can draw a line. That's the one we just saw. It's very simple. I just draw a line. It can be this line. This is from Muhammad. This is from Cherif. This is from Umran. This is from Bashir. Different line. But this one is not equidistant. I will not take that. So I will go for this line, which has been drawn by Fazar. So you can see that it's equidistant to this side. So this is going to be my optimal hyperplane. This is going to be my optimal hyperplane. Now, once I get that, I say this is linearly separable. But what if the data set is too hard, Shabab? The data set is too complicated, like this case. You try to solve it easily, but then you cannot draw a line. Look at this, red, blue. Here, there's a problem. I have blue and red here. This is called non-linearly separable. Non-linearly separable. So we use non-linear SVM to solve this problem. You see? So how do we solve it? We need to map it to higher dimensional space. This is the power of support vector machine. And that is what we call kernel trick. Pick it, Shabab. Kernel trick. This is the trick of support vector machine. He said, don't worry. What I will do for you, I will put this guy to higher dimensional plane. It will become solvable. Like the analogy I showed for you. If you cannot solve a problem at lower dimension, move to higher level, you can solve it. I'll give an example to demonstrate in a human life. If I want to categorize you, Shabab, in this class into tall, somebody who is tall, and average height, it's a linearly separable problem. I can easily do it. I just need to say, everybody stand up. And I can say, okay, you, anybody who is not up to 6 feet, you are average height. If you are above 6 feet, you are tall. Go here, go here. You know, I can easily separate everybody. Even Mohammed can just help me separate them. Oh, Dr. Adam, we have three tall guys in this class. We have two certain number of average guys. This is called linearly separable. Because by mere looking at you, I can separate you into two groups. This is linearly separable example. However, Shabab, if I want to separate you to who can run, and who cannot run, how can I do this? I want to categorize you into you can run, you cannot run. Can I just look at your face and say, I think you can run, I think you cannot run. I cannot do that. Otherwise, somebody can accuse me of being, how can you say I cannot run? Mean that I'm playing football. You are not correct, doctor. I say, okay. What do? I will ask all of you to run from the college building. I'll give you a task. You run from college building. You go to the vice president office for research, and then you come back to my class within few minutes. Everybody start running. And I gave you time. Anybody 10 minutes? I said, okay, go to this side. You come back after 10 minutes, you go this side. So at the end of the day, I can see people who can run faster, and I can see people who cannot run faster. You can see that I'm able to separate you. What I have done to make it possible to separate you is that particular task of running a particular distance. That task is known as kernel trick. Something that you do to something that ordinarily you cannot separate it now, but when you do it to those data, the data will go to another level and you can separate them without any. So this is on one-dimensional plane, x-axis. What I do to this problem, I make it to become two-dimensional. You see, I turn it to be two-dimensional problem. I give it x-axis. Even though I don't know what is going to be my y, we say y is equal to x squared. So this is our kernel. This is our kernel function, in this case, kernel functional. So what we do, for every value, we get the y equivalent. We scale it. So when I scale 2, it becomes 4. When I scale 3, it becomes 6. When I scale 4, it becomes 16. When I scale 5, it becomes 25. When I scale 7, it becomes 49. You can see that they are rising. I'm making a plot of them. This side also, they are rising. So finally, what do I get? Can you see a line between them? This is the same data. The same data said that we cannot draw a line between, but when I subject it to second, because it was on one dimension, this is only one dimension, x-axis only. Now I made it to become two dimension, x and y axis. Can you see? We can draw a line between them. We said it becomes linearly separable. This is the unique secret of support vector machine, Shabab. If you go to my Google Scholar link or my ResearchGate, you will see that so many of my research work, I use support vector machine alone. Since I detected this interesting algorithm, subhanallah, it is so powerful that if you cannot get it separated in the first dimension, you take it to two dimension. If it doesn't work in two dimension, you take it to three dimension, X, Y, Z. If it doesn't work, you keep pushing it up until you get your result. This is the big secret of support vector machine. It has always worked in almost all situations I apply it to, except in very few cases. Because like I told you, machine learning is not a dogma. There's no machine learning algorithm that can work in all situations. No. But I'm really telling you that this kernel trick has made support vector machine to be very, very powerful. And this is the secret behind nonlinear SVMs. So what does it do? Look at this line, look at this data, Shabab. Ordinarily, we cannot draw a line between this data. It's not possible to draw a line. When you put the kernel function, we've got the kernel function, look at what it does. The kernel function will push your data up to another dimension. It becomes separable at that dimension. You can see non-linearly separable at this level, linearly separable once we use our kernel function. The problem now is what kernel function I'm going to use. To separate who can run and who cannot run, I ask you to run. If I want to judge who can hit a big food or who cannot hit a big food, I have to subject you to another test. This is why kernel function work in different ways. And that is why one of the optimization parameter, one of the hyperparameter to check and optimize is the kernel function if you are using support vector machine. And it's the number one that you should check because it's very powerful. It will determine if your system will work or not. And we have several kernel, like polynomial kernel, like Gaussian kernel. You can also come up with your own kernel, like I gave you an example where it's got to SKR, but then it might not work. It might not work for many systems. You see, but we just use it as an example for you. But then you can come up with your own kernel function actually, as a machine learning student. Can I design a kernel function that can work for even better results? The kernel is a function that maps the data to higher dimension, where the data is separable. So the work of the kernel function is to map your data that is not separable at this level to a level that is going to become separable. The kernel helps us in projecting the data to higher dimensional space where the point can be linearly separable. Because you always remember that the secret of support vector machine is that every problem can be linearly separated. So if we cannot do it, it will convert it using the kernel to change it to a form that it will become linearly separable. This is another look at it again. Can you just see this, Shabab? Can you imagine this? There's no way you can draw a single. We want a single line to separate this data. It's not possible. We use a kernel function. Look at what happened. See? The general idea of support vector machine is the original input space can always be mapped to some higher dimensional feature space where the training set is separable. This is in 2 dimensions, X and Y. This is X and Y axis. What do? We take it to 3 dimensions, X, Y, and Z. Can you see data that was not separable before, Shabab? Sorry. Can you see? Totally separable now. The same data here that you cannot separate by line, after we apply appropriate kernel function, look at what we have. It pushed this one here and pushed this one here. This is the power of support vector machine. And it has continued to beat imagination of a lot of researchers. And as we are going to mention, it is not affected by even cost of dimension, which is making it very unique, actually. Cost of dimensionality doesn't affect support vector machine. Ajib, which is that when you have a lot of data set, you have a lot of data set, sorry, you have few data set, but your number of attributes, the number of attributes you have is more than the number of samples. This is going to cause you what we call cost of dimensionality, ordinarily. It means which is that you need exponential increment in the number of samples to be able to get something reasonable, but now you don't have data. So this problem is called cost of dimensionality. And the solution to it is feature selection. You have to do feature selection. Whenever you hear cost of dimensionality, the solution to it is feature selection. Pay attention to this. That is, in cost of dimensionality, your features are so many, but the number of samples are very few. In fact, in some cases, the features are more than the sample. You have like 50 features, and you have 26 samples. How can you get good results? So we said the solution is you have to do feature selection. But surprisingly, support vector machine, even in this situation, still get reasonable accuracy or result. Look at another example, Shabab. Look at this data, how clumsy the data is. This class totally surrounded this other red class. But with a kernel, look at what we turn it to. Can you see? Ajib. See, the decision surface became very possible to draw. This is the power of kernel. We call it kernel method. So the secret behind support vector machine, anybody ask you, it is called the kernel trick. Just tell the person kernel trick. That's why some people call it kernel. Some people call support vector machine, they said the kernel machine. Some people call it kernel machine. Because the secret behind it is kernel function. Now, so the nonlinear SVM, the kernel trick, instead of explicitly computing the lifting transformation, you define a kernel function that can lift the transformation for you. So instead of saying y is equal to x squared, we just have a kind of kernel function that can help us with the transformation. So we have the dot product, this giving us a writing to the nonlinear decision boundary in the original feature space. So this is an example. So like this, this is what our kernel, the mapping is going to be. You map x to become x squared from 1 dimension to become 2 dimensions. So instead of solving it explicitly, this is what we're going to have as our implicit. It means for every value you give to me, I'm going to transform my data into this format. And that is one problem with support vector machine, why it is computationally costly. It is computationally costly. Imagine every data you have to convert it in a kernel. You see, that is the big challenge. So that is another reason why, apart from the quadratic equation, it has to solve. The quadratic programming problem, it has to solve in an optimization manner. It also has the problem of computing kernel transformation for every input, which is another way of getting that high computational requirement. So there are a lot of non-linear SVM. We have the linear SVM, we have non-linear SVM, and we have the kernel function. There are so many kernel functions. The linear one, the polynomial, the Gaussian, the radial basis function. They say this is popularly used in image processing. This one, if you don't have prior knowledge about the data, you don't know how the data looks like, then this is a good option for you to use. This one is widely used kernel method, suitable if no prior knowledge also. However, these are all just examples. These are just examples for you to be able to indicate. Always remember my statement, LDS, about let the data speak. You need to let the data talk to us. So these are just advices, but sometimes it might not work. So the principle is let the data speak. So you have to do optimization for your kernel options. Use polynomial, use Gaussian. In fact, the first thing to check is the kernel, because that is the brain behind support vector machine. Once you optimize and get the best kernel, you can then check for C, the regularization factor, before you go to other minor hyperparameters. The nonlinear data. So SVM are trained by maximizing the margin. We have discussed this concept. So if the problem isn't linearly separable, there's no perfect decision boundary, so there's no hard margin of SVM. Initially, there's the concept of hard margin SVM. Let me clarify one point here, Shabab. Since we have linear SVM and non-linear SVM, I've seen students, they try to use LSVM. LSVM is a very popular linear SVM. But to me, it is disadvantage to go and use LSVM. What if your data is not linear? See, because linear SVM assumes that your data does not need kernel. What if your data is complex? This is why we always recommend that you use non-linear. You have nothing to lose. If the data is linear and you use non-linear SVM, it will make your result even be better. But however, if you go and use linear SVM and your problem happens to be complicated problem that is non-linear, you might be having very bad results. So this is a point I want you to take note. That is why anytime you are solving a problem using SVM, go for non-linear SVM. If then your problem is linear, yeah, you have nothing to lose. You only end up getting better results. Now, so there's the idea we discussed before that, okay, every group has to belong to this downside. See, this is called the hard margin SVM. We don't want anybody to have any class to be misclassified in the training. Usually we don't want this kind of requirement, because it can lead to overfitting. Rather, we have what we call the slack variable. This is the slack variable. The slack variable allows that when you draw the hyperplane, we allow one or two classes from one class to be in the other side. That is, we allow for misclassification. You see, we don't want to get 100% accuracy in the training. It's okay just to have one mistake like this. That is fine. So this is called soft margin SVM. The other one is hard margin. Everything you must belong to your class during training. No, it's too hard a condition. Sometimes you might not be able to achieve it. But at least once majority are in their normal classes, that is okay. You're getting 95% accuracy for training or 97, 92, it's okay. It's better than getting 100% accuracy for training and then getting 50% for testing. What do we call this problem? This is overfitting. You see, when you have excellent results in training and bad results for testing, we call it overfitting. There is a memorization. Your system has memorized. But when you train your model, you are getting 20% in training sets and also 20% in testing set. The results are both poor. Poor in training, poor in testing. This is called underfitting. It means you did not develop your model very well. It doesn't understand the problem you are solving. That is called underfitting. I hope that clarifies. These are very important concepts that we all need to pay attention to. Now, so the slack variable we introduced is just an idea to tell you that, okay, support vector machine also allow you. It's not that in all cases you have to get 100% during the training. No, the slack variable is allowed that, okay, this guy can be here. So this one also, instead of being outside, you can even be on the margin sometimes. So this is a kind of a slide variable allows, if the slide variable is 0, the point was classified correctly and by enough margin. So however, if it is between 0 and 1, the point was classified correctly, but by less of a margin. You see, but if it's more than 1, the point was misclassified. You see, if the slide variable is more than 1, okay, we allow misclassification to other classes. Once out of many samples, it is okay. So this is the idea. This slide variable led to the idea of soft margin SVM. Now, so this is the nonlinear classifier mathematically. So it's a similar thing, but then because of the nonlinearity, so the slide variable n can be added to the following misclassification of noisy example. So we introduce that slide variable. The slide variable now comes in to what we did earlier. So make a big difference. Okay, sometimes we can allow it. C is the user-specific positive number that we can give. Why this and this are the Lagrangian multipliers, the unconstrained cost function will become exactly what we written as before. Now, the next thing, very important thing I want to mention, Shabab, is the concept of hyperparameter. Hyperparameter is very important. Hyperparameter. Hyperparameter, they are the parameters that affect your model. Now, you know, in programming, we have parameter, ordinary parameters. When you write a function, you send parameter to the system, and you can easily see, okay, this is the parameter. But there are some parameters there that directly affect how your algorithm works. Those are called hyperparameters. So, for example, let me share something with you. So let me show you. I just want to clarify. This is our IBK. Now, you can see many parameters. These are all parameters that will get value from you assigned it to the function, okay? But among these parameters, if you close it, you see k nearest number tells us that k is 1, and then the Euclidean distance is used. These are the hyperparameters. This is a parameter. They are not very important. They are just setting some environmental value. For example, number of decimal places. This is a parameter to be sent to that function. However, among these parameters, the hyperparameters are k, the number of neighbors, and also the kind of distance function you are using, Euclidean distance, Euclidean distance, Manhattan distance. These are called hyperparameters. In case somebody asks you, what is the difference between hyperparameter and the normal parameter? So hyperparameter, they are the parameters that have direct effect on the machine learning algorithm themselves. So this is the concept of hyperparameter. Now, we continue. Can you see my... So you see the kernel, this is very important. I say it's number 1 for you. This is why you start. You can see that support vector machine is made of 2 things. Support vectors, those points you detected during the training, and kernel. In fact, the main guy is the kernel. That's why we call it kernel machine. Some people call support vector machine kernel machine, because it is the secret behind machine learning that makes it to be performing so wonderfully. So the second one after that is regularization. We have the gamma, we have epsilon. So let's look at it briefly. Now, you can see here. So when you optimize for kernel, already told you, I gave you different type of kernel, which is polynomial, Gaussian. You put polynomial, you run the experiment. You push it into Gaussian, you run the experiment, then you select the one that gave you the best. Now, we look at the regularization parameter, which is the C. This is the effect of the C. See? Here you can see here. This is you set your C, and this is tolerant. This is kind of, we draw a line. We tolerate some outlier points. Some guys are falling to the other side. That is fine. We want it, no problem. You see? Here we're trying to achieve zero tolerance with perfect partition. Can you see what we are doing? We don't want this guy. We don't want any mistake. So the separator provides the best classification, but it's difficult to train a model like this. This term is known as regularization parameter. You see, this is a wishful thinking. We want to get everything, but then how can you train a system like this? No. Our regularization parameter will help us to guide us. How are we going to do it? Now, so this regularization, the most important one is the C. Here, SVM want to achieve an upper plane with the largest minimum margin. You see? A hyperplane that correctly separates as many instances as possible. But the problem is that you will not always be able to get both things. You know, we are looking for largest minimum margin. Can you imagine? We're looking for largest minimum margin. How is that possible? So it's a condition that we want to maximize it, and at the same time, we want it to be the minimum possible so that we don't also have computational complexity. So the C parameter determines how great your desire is for the later. That is, how much of minimum margin can we have between the two classes? See, we want a large margin that separates them, but then we want them also to be, how is it going to be between them? Now look at this. If you see a low C, your C is very low. This is what you get. You can see you have a maximum margin here, mashallah, but then you make a mistake here. Neglect it as error. You ignore one, because if you want to follow this guy, then your line needs to come this way. And at that point, this is going to be support vector. And this guy is like an outlier. So you see, you are making an outlier to be a support vector. Then your system might perform badly. That's why support vector machine, once you look at the system, it tries to draw a line that makes more sense. This guy is a mistake. Halas, you are going to disturb my system. We ignore it. If you make your C to be large, it means you don't want to make any mistake in your training. So the system will force itself to come here. Because of this guy will become your support vector. And this guy is a bad guy. You can see now he's taking you closer to this guy, more than majority guy here. And this guy might be an outlier. This is when you're large C, when you have a large value of C, you cannot into the trouble, Shabab. We say a lower C gives higher error on the training set, but find a larger margin that might be more robust. You can see? So when you use lower C, here your training, you have an error. Your training accuracy might be 96% accuracy. But for this guy, we get 100% accuracy. You see, mashallah. But when you are going to do testing, this guy, imagine something comes here. You can classify it here because it's too close to this guy even than this guy. It will be a big problem. So it's better to make a mistake at the higher, at the lower level. In the train, a little bit of mistake, 96% is okay, than getting 100%, which will be termed as overfitting. Now, however, low C or large C, what is low is relative, what is large is relative. And that's why, again, you have to let your data speak. You need to put the value in and then check it and see the one that works for you appropriately. Still on the regularization, you can see here, this is another possibility. Look at during the testing, see if your C is low, look at the possible scenario now. For C that is low, this is a possible scenario. And low C will give you something like this, large C. So classifier learn using a large C value is best. This is according to this problem. But look at another case too. For this case, classifier learn using low C is best. This is exactly what I used to tell you, that the principle of let the data speak, Shabab. Can you see now? That is why advice could be given, but you have to let your data speak. When we use large C, look at what we are getting. We got better results here. But when you use large C, you are getting worse results here. Low C is working for this problem. Large C is working for this problem. This is why I always tell my students, let the data speak. Use your data, run the experiment, try a different value of C, record the values, make a plot, and determine the one that gave you the best result. And that's going to be the one you are going to be using finally for your. So that is telling us how this system works. So we are going to stop here.